So, hi everybody. It's November 22nd for the Rust CTCFT meeting. And let me see here. I'm just going to give a brief intro. So I wanted to say that this meeting was organized by the CTCFT team, especially Forrest and Technitos, and Jane Lesby did a lot of work pulling this together. And I wanted to give a thanks to Josh Triplett also for helping to liaison. So our agenda today is a little different. We're going to hear from 3 people involved in the Rust for Linux project, and they'll introduce themselves in a minute, I think. And the idea is that we'd like to be talking to people who are putting Rust to use in new, interesting, and especially extreme ways, and hear how it's going and what kind of problems they're hitting, what we might be able to make better for them. And that, I figure, can then factor into our prioritization process. And so I'm particularly excited to have them, have the ability for them to address all the teams, since I think there's probably issues that relate to the language, but also to libraries and to tool chains and all kinds of things. So we've asked them to kind of focus, not focus on this sort of thing. What might they want, or what might be useful to them, as well as giving us a kind of overview of how Rust for Linux works in general. So after that, there's going to be the social hour, and we'll handle that as we usually do. Jane, are you here? I'm not sure, but if not, that's all right. Which means we'll make a few breakout rooms and people can chat. If you have ideas for specific breakout rooms, please do post them in the Zulip stream, the CTCFT stream, and we can accommodate them. Okay, so I'd like to just take a few minutes if people have any announcements before we get started, kind of give an open floor. I have one, or yeah, I don't think Doc Jones is here, so I will give it, which is that Doc Jones and I are planning to host or organize this Rust-C reading club, our second attempt, since the first time we kind of underestimated the amount of demand. The idea is to have a sort of smallish group of people that will read the source code together and learn and share knowledge. And the first time we tried it, we had 100 people show up, and I couldn't even join the Zoom room, so that didn't work so well. So this time we're going to make a smaller list, but I want to encourage especially people here who do know Rust-C to some extent already, who might be interested in sort of running their own events, to get in touch with me, because I think the best way for us to scale this up is probably going to be to have more than one flavor and experiment with doing things differently and so on. So that's my announcement. Does anyone else have any other announcements? If so, feel free to come on camera. Okay, hearing none, which is good, or which is fine. I will say this, the way we usually run these events, I didn't say it initially, but of course we're abiding by the Rust Code of Conduct. And what I'd ask is that if you're not speaking, keep your camera off and keep yourself muted. But if you do want to speak, you can turn your camera on, and we'll see that and kind of call on you if you'd like to ask a question or something like that. If you don't want to turn your camera on, you can post something in the chat. Or raise your hand if you can find it. That's under I recently discovered that it's under the reactions menu. I'm not sure if it always was, but it is now, if you want to raise your hand in Zoom. All right, without further ado, I will turn it over to Rust for Linux. Let me stop sharing my screen. Actually, what I'm going to do is give you permission to share yours, because I realize you don't have it. Wait.
To Wesson, please.
Yeah, can you give it to me, Nico?
Yes. You should be able to share now. Is it working?
Yeah. Oh, yeah. I don't know if we can see. I see it as a wide screen. I don't know if the slides will fit or not. I guess it's fine. I don't know.
Yeah, it works for me, but I have a wide monitor. So.
Yeah, I think it's correct. Yeah. Okay. So, the first thing, thank you, Nico, Josh, etc., for organizing this and inviting us to be here, because I think we believe it's great to be able to have a bridge to the different Rust teams and speak about the things that we have found not lacking, perhaps, but things that we would like to see in Rust, perhaps. Nico said that this was also an introduction. We have not focused that much this presentation on being an introduction to Rust for Linux. We will focus on basically features that we would like to see in Rust and different problems that we have seen or faced and possible solutions, perhaps. So yeah. Also, thank you all the other people that have helped the project so far. I always mention this because it's we are here, the three of us, but there is a lot of people that have helped in one way or another. Also, let me preface that we are not Rust experts. At least I am not a Rust expert. So if you find that you have solutions, even if they are obvious, just let us know. Sometimes for some of these features, we have alternative solutions or workarounds and things like that. But what we are trying to do here is to ask for what would be ideal, right? Or to see if it can be achieved or not, etc. Okay, so Rust for Linux, as you know, most likely know and you have seen, is trying to add support to the Linux kernel. To add initially for modules, for kernel, what we call not Rust module, but what we call kernel modules. But probably later we have seen already people motivated enough or wanted to have this go all the way and have Rust even in core parts of the kernel. We believe that Rust offers key improvements overseeing this domain, and that's why we want to see it happen. We think the end result will be a much improved kernel in memory safety and other domains. And yes, let's start. So the first thing to take it out of the way is nightly features. Nightly features, of course, we use some nightly features, and there is a general priority or a general goal that we want to have that is stabilize or find alternatives to those nightly features that we already use. There is a link there to the live list of features that we currently use. We want to build the kernel without exploiting or abusing RUSI Bootstrap. We know, we should perhaps not be using it, but it's the way it is. We want to target, for the moment, official or full releases or tagged releases of the compiler. That's how it works for VCC and Clang. Yes, we for the moment we use nightly features as minimizing them where possible, and hope that in 1 year, 2 years, we will be able to, as soon as possible, build the kernel without a state. There is a list of features that we currently use. They are not that important to discuss, but the rest of the talk will be focusing on things that are not in nightly yet. So things that we cannot just say, well, let's enable this feature and that's it.
All right. So can you hear me?
Yeah.
Thanks. Here I'd like to start talking about pinning, which is a sore point for us and a source of the major source of unsafety in the drivers that we port to Rust at the moment. So we are very motivated to see improvements in this area. In this section, I'm going to talk about three things, right? I'm going to talk about the initialization of pinned objects. I'm going to talk about projection of fields of pinned structs. And there's this other thing which is not really related and could be solved, addressed separately, but it usually appears in the same context. right? And it's the definition of lock classes for lockdep in the kernel. Just as a bit of context, the kernel has this debug mode that at runtime it tries to prove the correctness of lock ordering, and this is where this comes into context. So the problem we have is we have a lot of data structures in the kernel that are self-referential, and they need to be initialized before they can be used. So what we have at the moment, and this is what this code is showing here, mutex is an example of this. We have a new method that creates a new mutex, but it's unsafe. And the safety requirement is that you call init lock before you actually use it. The call to the C function that implements this is here in the init lock method. This is how C does the lock class creation. It's actually, it defines a macro and defines a class here, static local variable, and gets the name from stringifying the input. This is an example of actual code at the moment, and you can see how polluted it is to actually create and initialize this struct that has two mutexes in it. We actually have unsafe blocks for the new. We require safety annotation, so we have to describe why it is safe, and we basically say we're calling it below. Before we can call it below, we actually have to project these fields in their node refs, which is also unsafe. And then we call the macro to initialize it. And when calling these macros, we have to manually specify the name. We can't just stringify pinned, for example, because pinned is meaningless. And these names are actually used when the log analysis code in the kernel finds a violation, and then it uses this string to report the errors to users. What we'd like to see is something like this, which is the expected ergonomics for creating things in Rust in general, right? Of course, there's a lot of magic here because it takes care of all the three things I talked about before. So we don't know if this is possible, but we'd like to get as close as possible to this. This is what we'd like to see in the end.
Yeah. Another topic is what we call the modularization of core and alloc. This means perhaps modularization, perhaps partitioning core and alloc with some config options, because the kernel doesn't need all the features that core and alloc provide. So configuring them off, at least, is important for correctness, for code size, even perhaps for performance. And this is very likely useful for other domains like embedded, safety critical, etc. The list of features that we don't need, some of them at least, are floating point. As you know, we already have upstream Rust already took that config option to basically remove part of the floating point formatting code. Also, big integers, we will not use them. Unicode, the Unicode tables, UTF-8 support, etc., etc. Also, another popular one is the infallible allocation APIs. We are using no global out-of-memory handling. Although some of the try methods are still missing, but that's fine. I think that's the CFG looks like a nice solution. There is also types that, even though we could, in principle, use them if we could somehow tweak the implementation or have some way of plugging some bit of them, we think it's and Wesson will discuss a bit of this later, that there are some types that we would like to implement on our own to use kernel facilities. For example, a mutex, instead of using the mutex code that is in core alloc, use the mutex from the kernel. So we'll wrap it in a type.
All right. So the next topic is the memory model, right? As you know, the memory model for unsafe code in Rust is not defined at the moment. And it's not a problem for us at the moment because we are not targeting writing code at the moment that relies heavily on the memory model for correctness. What we are doing, and this is an example of how we do this, we actually we use the C implementation at the moment. So in this example here, we have a sequence log, which is backed by the C implementation. And here on the right, we see the ARM64 output for this loop here, right? And you see that we have the memory barriers here, and it's a load barrier, which we don't really have in Rust. And with LTO enabled, which is what we have here, we get code that is as efficient as C. So although memory model is not a concern for us at the moment, we'd like to talk about this for the future, right? So as some of you may already know, some may not, but the kernel has actually a different memory model than C, right? What we'd like to see in Rust. Go ahead, Nick. Do you have a question?
Can I ask a question? Yeah, actually on the previous slide.
Yep.
Just so I understand here, you have the sequence lock, spin lock example. First of all, there's only one lock going on, I guess. Is that right?
So the sec lock allows you to access the example for reading without acquiring the spin lock. That's what it does. And then for writing, you need to acquire the spin lock.
And that's why you have the atomic U32 fields and not just U32?
Yes, exactly. Because you can actually have writers and readers concurrently accessing these fields, right? It's just that if while a reader is reading, a writer modifies, we'll realize it based on this need retry, and then we come back up and then we try again. And with this, we get a consistent view of the two fields.
Okay, and nothing in the current setup prevents me from misusing the seek lock API and saying v.read, but actually doing writes. Is that correct?
That's correct. Nothing prevents you from doing that, but there's actually a sanitizer in the kernel that we can invoke that would catch this at runtime, right? But there's no facility at the moment to actually prevent that. If you actually have ideas on how we could prevent that, those would be welcome for us to try to claim that we are better than C even in this sense. But yeah, the idea of the sequence lock is kernel data structure, right? It's used in a few places.
Understood. Okay, thank you. That helps.
Yeah. So coming back to the future, what we'd like to see is that not only Rust define a memory model, but that the memory model that it defines is compatible or somehow unified with the Linux one. So there's no need for the kernel code to bolt assembly definitions onto the code and define a new memory model that way. Another thing is in C. The kernel doesn't understand, not the kernel, the compiler doesn't understand address and control dependencies. So they are sort of fragile at the moment in C. What developers do is they use these dependencies to avoid having to use the heavier weight memory barriers. And then they look at the assembly code in the end, they generate the binary in the end, and check that the chains have not been broken by optimizations. That's sort of what they do manually. But this is, of course, very fragile because a change in the compiler can result in incorrectness in the code. And this is where we have a great opportunity in Rust. Is if we could actually have the compiler understand and honor these chains of dependencies, then we could actually have Rust be better for writing this sort of high performance synchronization primitives and algorithms for core pieces of the kernel. As an example, due to this fragility of optimizations potentially breaking things, when LTO is enabled in some architectures like ARM64, we actually fall back to a much heavier weight, barrier, an acquire barrier every time we read something to ensure that we don't break chains. So in Rust, not only could we be better in terms of the ergonomics of writing these things, but also in performance of the code at runtime. Back to Miguel.
Yeah.
Sorry, one more question on that.
Sorry, Nico, go ahead.
Yeah,
to go back.
Just to understand. So the what you're saying here is that the kernel and C have different, like the natural C memory model. I guess I don't quite understand why you're having issues with C.
Yeah. So the C memory model actually came after the kernel one. So in the kernel, the barriers that we have are like read and write barriers, for example, right? But if you look at the C and Rust, since it sort of inherits the C one, there are no read and write barriers. There are load and acquire barriers, which have different semantics, right? Acquire is a semi, as you probably know, it's semi-permissible, right? Certain things can go above and below it. The same thing with the reads and the read and write barriers, but they're permissible in different ways, you know. And then things like sequence lock, for example, since they require a read barrier, they cannot be implemented using the C semantics because there is no read barrier, right? You'll have to use heavier weight barriers like sequential consistency, which are much heavier than needed. So the code in the end wouldn't be as efficient. Now, in addition to these barriers, there are different, right? There are cases where you can exploit these dependencies, control or data dependencies between loads and stores to have implied barriers. And the kernel does that. The problem is the optimizer in C is not required to honor because it doesn't know about this, that we are trying to exploit that. So we actually may break these dependencies. So the processor will reorder things and break things. And then LTO exacerbated this problem by doing these optimizations at link time. So they had to actually use the heavyweight barriers to prevent it.
Okay.
Does it make sense?
Yes, it does. And I guess that workarounds there is a link where I could learn more. Is that right?
Yes. The workaround is a commit.
Yeah, excellent. Okay. Thank you.
Yeah, this is a trivial one. Basically, the tooling around Rust ideally should avoid cargo. And we don't want to get here into a discussion of cargo, no cargo. Basically, cargo is a great package manager and build system. But in the kernel, currently we don't use packages as such, and it has its own quite involved build system already. So any tooling that assumes cargo, basically, that there is some cargo or the way of describing organizing Rust code in the file system, that means is problematic. For example, one was Clippy, which I requested to whether it could be added officially in the documentation or supported the use case through Rust C directly, which is how we use in the kernel. And it was fixed. That was great. Build STD is another one that I will talk later. There is also, for example, MIDI. MIDI currently is only supposed to be used through cargo. You can, of course, use it if you know the right incantations, or you reverse engineer the thing. But ideally, it could be like officially supported to run without cargo first, and then perhaps we can give it support to run in the kernel, and that would be great.
All right. Now I'd like to talk about three cases of const uses, const context. I'll try to go faster now because I think we're running behind. So the first example of the three that I'd like to show is how device ID tables are generated in the kernel. If you look here, we have a struct which is defined by the bus, right? There's an ID, a mask, and there's some arbitrary data, untyped data here that drivers can specify whatever they want. And this is how they build it. They have a zero terminated array with all the IDs that they support. And then we have this macro here that actually puts this table in a section that tools can actually look up offline. And this is how tools check if to search for drivers that implement search for files that implement drivers for a given device when the device shows up, and then can load the device and use them. And this is why we want to have this in Rust, so that we have the ability to do the same in Rust modules. This is how we do it today. At the moment, we have a macro as well to define this. And what we want here is a const function to create from this, which is a typed version of that ID, the raw one, the C version of the thing. And here is an example of what we could do today, but there's a bunch of reasons why this is not enough for us. I'm not gonna go into them. We can talk about them later. This is another example of what we'd like to see with the semantics, with the ergonomics that we'd like to see. But there are a few things missing, like we can't define const functions in traits. If we do this, where we have a const, and then that const is the size of an array, it says it's unconstrained, and there's a circular dependency. If we add a constraint here, bound here, 0 is not allowed to be called from const context. And So at the moment, we can't really do the trick where we compile this and we have a section with the zero terminated raw IDs in there. This is the second thing I'd like to wait. There's a question there. Am I right at procedure? Yes, we're trying to avoid procedural macros. We can talk about this later, but we're trying to avoid them.
We tried about them, but they are not out of the question. I mean, we have from macros already, and we use them, so we can use them fine. They don't need cargo, so it works fine. Yeah. It's just that we try to avoid them, but we can use them when it's needed. Basically.
Yes. So the second example, const related, is simpler than before. But the idea is in the kernel we have lots of these vtable-like structs that have a list of functions in them. And in this case, we actually also have a pointer to a module, which is basically the library that implements the functions that we have pointers for here. And the way in which this is used in the kernel is if you load a module and that module provides a file, in this case here, and the file is opened, okay, then the ref count on this module is incremented. And then if you try to unload that module, then it fails because somebody's still using the module, and you guarantee that the file will not jump to some position that was unloaded. And this is how they're used. You see the static const here. The problem that we have at the moment is that Rust doesn't allow us to define a const and within that const have a pointer to non-const data, and this is the error that we get at the moment. So what we'd like to see is some way to do this, to have a const. Oh, and the reason I failed to mention this, but the reason we want this to be const is because that's a vtable, right, with function pointers in them. So we want that to be read-only, such that if there are vulnerabilities in the kernel with arbitrary writes, they cannot write to this vtable and then escalate that from arbitrary writes to arbitrary execute. So basically trying to reduce the attack surface in the kernel by keeping that in our raw data. So anyway, we're looking for ways to do this. At the moment, we don't really have it. The last example of const support is this way. Like we're trying to in the kernel we have a lot of instances of things like this, where we have a memory block that represents a device, and this memory block has registers for that device, and you can write to those positions. And these are of a given size. For example, a page, so 4K. And the offsets within that struct are usually known at compile time as well. So we'd like to, if the offsets are known at compile time, we'd like to be able to just access them without having to do checks at runtime. And this is how we accomplish it, right? We have this self OK, and we have a check here, and we do a build error if it's beyond the size that we know about. And then what we do to catch this is we don't compile in this build error, and then we get a link error when we try to compile this, which is better than C, because then we catch these before, and we don't produce a binary that has this bug. The problem though is that for unoptimized builds, we need to keep this build error in, otherwise we won't be able to run this. So we don't get the compile time error, and then this panic happens. It's turned into a runtime panic, which we'd like to avoid. And the other problem is, here's the example of the build error that we get at the moment. We get this line number and file name here, which are not really the source, the real source of the problem. And we have this mangled function name here, which is helpful, but it's not as nice as something like this, or where the real problem is. So we'd like to be able to get better error and suggest the use of try. This is one thing that I didn't mention. But if the offsets are not known at compile time, then we can't do the check at compile time. And then we force users to use the try version, which has a runtime check. And if we have time in the end, I'll talk a little bit more about how we'd like to improve these try versions. That's it.
Yeah. Another topic, general topic, is architectures and GCC support. As you know, we are constrained by LLVM architecture support, and on top of that, the support of LLVM in Linux itself. We currently support, for Rust for Linux, we support a few architectures with some constraints that may or may not go away with time. But the main point is that GCC support would alleviate this point. Yeah, I mean, whether it's with the RASI, Codegen, GCC backend in the RASI compiler, or with the new GCC Rust frontend for GCC. There is also binding, the question about binding. And binding, even if we manage to have full GCC builds, by full I mean in the C side and also in the Rust side, with, for example, RASI, Codegen, GCC, we would still have binding, which does not have a backend for parsing the code with GCC. This could be important, especially if, for example, somebody is using a plugin in GCC that, for example, say reorders the memory. So not the memory, the members of fast track, right? It's not a big deal. It's not a big deal, I think, nowadays, because there is discussions in the kernel about basically removing all support for any GCC plugin. But still, it would be nice to have the binding support in a GCC backend. Then the target specification. So right now, well, as you very well know, normally users of RASI use the built-in targets. Most of the people use the built-in targets, except perhaps embedded projects and so on. And the kernel, the thing is, the kernel normally tweaks targets in one way or another, and may want to switch some options here and there over time. So in general, we would like to avoid, even if we could submit all the possible combinations of targets that we may need to run upstream Rust, we should anyhow avoid a circular dependency between the kernel and the compiler. Also, custom targets are not stable, and as far as we were told, unlikely to be due to what they are too tied to LLVM configuration that RASI does, and also not all the target options are available or exposed through that target file. For example, the RefParm for Intel architecture. Yeah, so for this, I mean, we don't particularly care whether it's done through files or flags, but in general, ideally, it would be great if RASI could take the same flags, even with the same names that GCC and CLAG have standardized on for all these particular options. And it would be also a nice way to stabilize it piece by piece over time in RASI's side. So you could stabilize this flag, then this flag, etc. Then there is here like a far-fetched idea, but we are trying to push it for it anyway, which is cross-language, cross-toolchain standard way of specifying the target, right? So we could even use the files idea from RASI, but try to get GCC and LLVM folks to accept this way of configuring a target. And then in the kernel, we could have a single source of truth to configure all the toolchain and also the projects as well. An idea, we already told some LLVM and kernel folks about this, and one possibility would be to bring everyone to this mailing list, the Linux toolchain mailing list, and discuss whether this will be feasible in some time. Of course, this will take a lot of time, but if we end up with a way that we don't have to, in the kernel side, hack in the build system, to generate a target file manually and then pass it to RASI, etc., then it would be great.
All right, so the next topic in our laundry list of things is the ability to implement our own ARC, or in general, any library types that use some magic from the compiler at the moment. We have here a list of things, reasons why we did that and consequences of that, but I'm going to skip it because we're short in time. The next thing is some ergonomics, things that you guys may be able to provide us with that would improve the ergonomics. So this is an example of how people would implement, and we've already seen something similar to this in the previous slide. People have to implement their methods here for this trait, but not only that, they actually have at the moment to do this declare file operations, but they have a list of methods that they actually want to have populated in the kernel file operations struct. And the reason we need this is because the kernel actually behaves differently depending on whether the pointer is null or non-null, right? So because you could imagine that we do something like, oh, the default implementation mimics the kernel, but we can't really always mimic the kernel for one thing. But the other thing is that it could get out of sync, and we can't always. Like for example, between read and read iter, what they do is if you have one but not the other, one calls the other. One is implemented based on the other, right? So we couldn't implement defaults that depend on each other because we get into infinite recursion there. This is the hack that we use today. And basically what that macro does is populates something like this to use. So what we'd like to have from you guys is in the const context. So this is also related to const. In a const context, be able to determine if for a given type, a method is implemented by the type, or if it's using the default implementation for the trait. If we are giving something like that, then we can use that to populate the kernel file operations and whatever operations table it is. And the ergonomics in the end will be better than in C. Now this is related to Rust analyzer. Again, we have an example of a trait and implementation of the trait. So the way we expect people to use this is to come here, do impl file operations for X, and then do the implement members method in Rust analyzer. The problem at the moment is that for this specific case, and a lot of cases, because this is a pattern that we follow pretty much everywhere, the type is wrong here. So this doesn't compile. This is the first problem. Now, if we had Rust analyzer fixed, it would expand to this monstrosity here, which scares C programmers. When they look at this, they're like, "Oh, what is this? It's S and these angle brackets." And some people call this a smiley face. You know, they really don't like this. Now, what we'd really like Rust analyzer to do for us is do this, right? And this can be inferred by looking at the type wrapper here, and it knows it's a box, and then you look at the pointer wrapper implementation of box and find out that the borrow type is really self ampersand self, so it's a shared reference to self. So this is what I'd like to see. We don't know if this is possible or how hard it is, but ideally that's what we'd like to see. A little bit more. If we can't get that, then from the compiler folks, what we'd like to see is in this case here, the fully qualified syntax. We would like to be able to avoid this, especially because the only bound that the wrapper has at the moment is pointer wrapper, right? So we'd like to see something like this, where we can go straight from self wrapper and borrowed. Again, we don't know how hard it is, but we'd like to see it. And the last thing in this list is the lifetimes, right? In the case of ref, which is our replacement for arc, it's probably not the best name. You can rename it later on. But it takes since it's a ref, it takes a lifetime as an argument. What we'd like to see is for these lifetimes to be elided, similarly to what we see with the ampersand, right? And then the syntax in the end would be something like this: ref borrow self, and we feel this is easier for C kernel developers to swallow when they're transitioning to Rust.
Yeah. So let's go quick here as well. So built-in STD, we are building STD for the test crate, which we use to run the tests, which run on the host, not on the kernel or on a booted kernel. So they run in the host, and it's currently hard, in between quotes, to build compared to core and alloc. It's hard, and there are several reasons why. Well, build STD on one side could be improved to solve a few problems, but basically we have a huge hack to use build STD and to be able to compile everything, and well, there are a few hacks there. It's quite useful. Perhaps for us, it would be even better to make tests not depend on STD. Somehow plug in the bits that the test part needs, so that we can provide them in the kernel, and then we can run the tests even in kernel space. And related to this, that is testing. We really like the approach that Rush took for testing. In the kernel, we have, apart from the host tests that we already support, we would like to run code in the kernel space, in a booted kernel, and also in a booted kernel run tests from user space to that kernel. So these are called key unit and self-test respectively in the kernel. And it could be the syntax could look like this, where you specify test, but what kind of test, whether it's in the host, in user, or in kernel. So the bottom two would be in a booted kernel, for example, in QM or something like that. Similarly, for RustDoc, RustDoc could also take this and allow us to run kernel code or user code that is supposed to, for example, to test a syscall, right? Then Next slide. Yeah. So there is a lot of ways to discuss this, and we don't want to get here into details, but there are several ways we can think of doing it. Let's not discuss it. A question is how to make it useful for other projects as well, depending on how complex the solution is, or if we just pipe out the source code. We ask the compiler to give us the source code for the test, and then we build, for example, a kernel module that we execute, etc., etc. So we should do discussion about this, I guess, offline, and we can perhaps see what we can do. There is another moonshot idea, which is REST analyzer support. After that is done, we could have REST analyzer as well, be able to just click and run the test, even in a booted, so boot QEM with that, build the kernel module, boot the kernel, put the module in and test the code, etc. And even attach GDB if possible. So there would be very, very nice features that kernel developers are not used to.
All right, so the next topic for us is the quality of Codegen. And one thing that we'd like to emphasize here is that we're not so much concerned about the speed, but we're concerned about the size and the appearance of the code. The simplicity, I suppose, is one way to put it within reason. So here we have a couple of examples. We're not going to get into the details, but this is a minimized version of a scope guard. So here, the context here is like we go to the kernel developers and we say, instead of having this spaghetti error handling of a bunch of go-tos, and in fact some go-tos backwards, in the kernel, we say you have the drop trait to take care of most of the things, and then in the cases when you can't use drop, then we have the scope guard thing here, right? And then we say this is zero cost abstraction, collapses to nothing, right? But then when we go in and look at the output code as to show them as evidence, because they actually ask to see this, they can say like, oh, show me the generated the binary. So we go there and we look at the thing, and we have this huge block here, and we have some no-ops that are implemented as moves and tasks and conditional jumps. And this is the simplified version, right? So this is what a kernel developer was expecting to see, and this is what we had to show. Which is unfortunate when we're trying to make the case that we can build this zero-cost abstractions. And then in some cases, we do get them, like here, and we get this if we use unwrap unchecked. But if we just use unwrap, then we get this other thing here. So it's a bit non-deterministic. This is another example. Don't need to go into details. It may look convoluted, but this is an iterator. This is an iterator. This is implementation of sequence locks using iterators. And again, this is what is generated. And if you look at it, we have unconditional branches implemented as conditional branches. So we have no ops again as tests. And this is the code that we'd like to see, and the code we see if we don't use iterators, if we write them linearly. Another topic we'd like to discuss is padding. And I've seen this huge discussion about padding, but let me just briefly tell you what the requirement is. The requirement is when we are copying data from the kernel to user space, or we sending it over the network, we actually want the padding areas of structs to be zeroed, or for a pattern to be written. What we don't want is for the contents to be arbitrary, because we actually may have secrets and data that we don't want to expose from the kernel or from other processes. For example, pointers, which would reveal addresses of kernel data structures. Those sorts of things we'd like to avoid. The next thing is the opposite direction here of the padding, but it's when we are reading. Of course, we have these types like bool that have specific bit patterns that are required, and different bit patterns that are different from those can result in undefined behavior. So we like to avoid that. And so what we did was we defined this unsafe trait, and we implemented for a bunch of the basic types. But what we'd like to see is that this is something akin to auto traits, where if you actually define new structs, new types based on these ones, then they will also be safe to read from bytes.
Yeah. Very quickly, this one is, as you know, some kernel developers put a value on having a language specification, like because the class reference for the moment is not complete or even normative yet. And I don't know if it is even, well, in the introduction, they say, it said that the reference is not intended to be a specification, but some kernel developers may ask for that. So we think we would like more effort to be put on more resources into the reference if possible.
So here is branded types as the Ghost Cell paper calls them. We know this is not going to happen overnight, but we'd like to see this eventually. And the idea here, this one is going to be briefer. I have another example next. So the idea here is we have this try write, which has a runtime check, but the offset that it's using is not known at compile time. That's why we need this to get try. However, it is known at init time. So what we'd like to see is that this is initialized once, and the offset is checked once during init, right? And then later on, when we use this several times, and this example comes from the NVMe driver, and this is in the critical path of the NVMe driver. So this is actually a place where these sorts of things matter. So what I'd like to see is that this becomes some branded use size that is tied to this bar here variable. And the idea is that you can only use this offset for this instance of bar, right? Not other instances of bar, because they can have different offsets and may not be valid. And here's another example of branded types. This is a made up syntax that I have here. And the intent is just to say that this is not part of the process type. This is that doesn't have to be repeated everywhere. But the example here is just RCU. RCU is similar to cyclog in the sense that you can access this thing for read-only without having to acquire the spin lock. But if you want to change it, you acquire the spin lock, right? And the idea here is that to modify it, you have to show evidence that you've acquired the lock for the spin lock, and you do it by passing a guard. But without branded types, somebody could actually lock a different process and pass a guard for a different process to this guy, and we would allow access. So the branded type would prevent that, would ensure that this guard actually belongs to the same process. And this is what we want. We can actually implement this at the moment with runtime checks, but this requires extra storage for us to remember what the process pointer is, and a runtime check for us to check that you actually have passed in the right cards.
Yeah, we are about to end now. So there is this bit of a research topic. We wanted to include one of these here because it would be nice to improve the state of the art compared to C. So as you may know, in the kernel, there is two main states where code may be executing in, with atomic and the sleep over context. In the atomic context, you cannot call functions that might sleep, or if they actually sleep, you cannot call them, because you may end up freezing the kernel entirely, or panicking, or etc. So the C side currently, basically the programmers are tracking this manually, and there is some runtime checking that you can enable, which you put in functions that might sleep. You call a function or a macro that tags them as such. But the question here is, could Rust provide compile time checking? And here the example is the case. So basically the bottom two would be okay, but the top two, if you call from a function that is called from an atomic context, you call as a sleep function or a function that may sleep, even if it is not always sleeping, we would like to see a compile time. There is two questions about this. One is inferring or annotating explicitly, or inferring whether a function may sleep or not. We could have something like unsafe, but automatically infer. Let's say we say color unsafe because this comes from an earlier discussion last year in last year's RPC, but don't take it as it should follow unsafe at all. But the question here is, we could have the compiler check all the calls that are done, and of course the devil is on the details of what happens with FFI, whether function pointer type should have the tag of whether something might sleep or not, etc., etc., etc. But it could be nice to automatically infer whether a function sleeps, and this is one side of the equation. And if we do that, we could even have a RustDoc like this. I did a mockup where we actually saw that the properties of this function where it may be unsafe or sleep, and we could show it in RustDoc. Then there is the other part, of course, which is the actual meat of the problem, which is checking what I said in the beginning, that from an atomic context, however is defined, and how we would do it. If you are in an atomic context, check that we don't call any of these sleep function. But even if we only had this, automatically inferring what is a function that might sleep, and we have it in the documentation automatically done, that would be quite an improvement compared to C, even if, of course, the C side could do the same eventually, but they don't do it right now. And finally, there are other things that we have put here. We have even more. If you ask us, we can perhaps come with more, but yeah, there was not so much time, so we have put here a few more. And that's basically it. So thank you for inviting us again. If there is any questions, please.
Well, that was really great. Yeah, does anyone have any questions? There was a lot of information there. So I'll give a minute for people to digest. But otherwise, I think we will go into the social hour. I don't know if you three are available in the next hour.
We should be available. Yeah, we should be.
Okay. Excellent.
Yeah, we tried to, we spoke with Forrest and Josh, and then, yeah, we took all the time for this so that we could then perhaps discuss in the social hour if folks want.
I had one question. You mentioned cargo wanting to avoid invoking cargo, but finding that some tools like Clippy or Miri or whatever kind of expected you to use them through cargo. I was wondering, is it really that you want to avoid cargo, or is it that you want some sort of way to integrate cargo or limit what it can do more easily into the build system?
So I would say the second. I mean, I don't know, I cannot tell, or I cannot say for all the kernel developers. I know some of them for sure would not like to see cargo, but others don't care as long as it works. So for example, one trivial problem is if we originally had the project using cargo, and we had problems, for example, with organizing the files, even something as simple as for every single module, because it's a different grade, you will have to put the source folder, etc., etc. So you have to have the cargo tom. So for every single, while the kernel developers, they want to write a driver and they just have to put a .c file. Okay, so that was one trivial case, right? Or the UI when you're running make in parallel, make is using several cores, and then you get cargo also mixing the output in between, and they may be using more cores than you may want, etc., etc. So there are few things that can be solved, and if everything is solved, and we can discuss. We didn't want to put it here because it was not a priority in the sense that we already solved it in another way. But if in the future cargo is possible to do with cargo, we will be fine with it. But again, the kernel build system is like quite involved. It's quite they have a lot of things there. It uses its own way to track mostly everything, and yes, so it would be. I mean, I don't know. I am not opposed to it, and again, we had cargo, but I think at least for the beginning, to introduce Rust to the kernel community, it's easier not to put cargo for the moment.
I think another.
But yes, we would anyhow, even if we don't have it for the kernel, we would want to see some of those improvements anyhow for cargo happen for other projects, or for even, for example, for building the user space tools that the kernel contains. So in the kernel tree, we also have user space tools, right, or scripts even.
I think another element is that cargo will not be the kind of end user facing thing, because the kernel build process is so involved. You have to, take your shared object and turn it into a kernel object and all of that. So it will never be end user facing. At least I don't think.
Yeah, that makes sense. So it's always going to be a subsidiary thing invoked by the make files or what have you.
Yeah, and actually now we are using. We even requested and for one. I don't remember. It was a year ago, but basically everything for us, the most important thing is that we can do everything through Rust for a moment. So that's why, for example, Clippy now support. They were kind to put the documentation. They said, yeah, it should be fine and supported. So we would like to see not just perhaps documentations or like just do it in some way, or find out the commands that cargo is running and then run them yourself. We can do, for example, for the build STD case. I am fine doing that. We are fine doing that because it's for the tests, and it's something that is not normally, or at least now, kernel developers may not be running all the tests all the time, at least the Rust tests. So that's fine invoking cargo for building the STD crate. But still, it's just that also if we are only using it there at the moment. So it's like a bit, we also kernel developers, I don't think they would like to see downloading of packages, for example, for building STD. So that's another point. So there are a few things there that will need to be discussed on how to,
Okay. Well, we're at time, so why don't we start off with we can move any further discussion into the social hour. I just want to thank all three of you again for that excellent presentation. And I'm going to end the recording. But, great job.